All right, so we're going to start on redox titrations. It's exactly what it says on the label. I mean, come on. It's a titration using a redox reaction, right? So a reduction oxidation reaction. Titrations before acid-base reactions, right? Just keep in mind that unlike acid-base reactions, where everything was always one proton at a time, redox reactions don't have that, okay? Redox reactions will be multiple electrons at a time usually. It could be one electron at a time, but it could be 2, 3, it could even be 4 electrons, right? It usually doesn't get much past that. I don't think I've ever seen a 5-electron redox reaction, but it's possible, I mean. It could happen. You'd have to have a hell of a charged state, though. I'm not sure what that would be. I think I don't remember any metals that go up to past 4+, so that'd have to be some sort of polyatomic, I think. Anyways, these are some of the different oxidizing and reducing agents. These are the oxidants right here. These are reductants. Okay. Notice that a lot of the vitamins are actually redox reagents as well. It's literally what they do in the human body, right? So you can also use the ones in the human body to do this. You can use ones that are metals. There's polyatomics. There's all sorts of things, right? You've actually kind of already done this a few times, though we didn't really do a titration. We just loosely did it, okay? You'll actually somewhat do this, though, in the... Oh, no, you won't do this one. No, I don't have time to have you guys do this, which is unfortunate. But you do an EDTA one, right? Good enough. Okay, so let's consider this titration right here. You have iron 2 with a standard selenium 4. You typically monitor these with a potentiometric or a potentiometer. Typically, you use one standard probe because remember, you can always correct for the standard, right? In fact, many of them do it digitally, so it'll automatically do it for you. You don't even really need to know what this is other than understanding under what conditions it works, right? Okay, so one will be a standard. One is typically a platinum wire because you want to reuse these. Why would you want a magnetic stir bar, by the way? What do you always need to do while you titrate? You should always mix it, right? Otherwise, you'll get pockets of where you have low concentration. In this case, we're putting in selenium 4+, and we have iron 2+ in solution with, in this case, a strong acid. These keep the CO2 from coming in here and precipitating things, by the way, is one of the things this does. It also keeps, remember, most metals are insoluble with a hydroxide, right? If you put them in with OH- basic solution, they'll precipitate out. So keep that in mind if you ever have to do this. This titration reaction is this overall reaction right here. So you have this going from a 4+ to a 3+, this one going from a 2+ to a 3+. So which one's being oxidized? How about which one's being reduced? C. Okay, the other one has to be oxidized, right? Okay. Fe? You can just say Fe. Yeah, iron. Cerium. Or cerium, excuse me. Though, honestly, CE would have been fine. I don't need to say the name. Oh, fuck, I don't care what CE's name even is. I have it here, sure, but who gives a shit, to be very honest. CE, right? You need the name, look it up. I couldn't care less. It is a oxidizing agent, right? So at your platinum indicator electrode, you'll have two reactions that will come to equilibrium. You have, of course, the half reaction of the iron, and then you have the half reaction for the CE. There you go. Okay. And they have E naughts, right, that you can get from books. Notice they're always put in the form of a reduction. Okay? Absolutely always put in the form of a reduction. By the way, a lot of times you'll see people use a one electron balance or reactions that match the electrons. So for example, if you have something that transfers 2 electrons, they'll match it with something that transfers 2 electrons and has a higher oxidizing potential. You understand what I'm saying there? Like this would not work well if you use lithium, right? Because it doesn't take electrons from iron. And so you would never transfer the electron, right? Okay. So you have several different regions, just like every other titration, right? All titrations are similar. You have little bits that you have to add on to the back and front, but that's it. They all have the same regions, they all have the same basic formulas, they're all the same fucking things. Because you're putting one species in to consume the other, right? In some way. Maybe you make a complex, maybe you make the acid, conjugate acid, maybe you reduce it, right? Or oxidize it. Okay, so before the equivalence point, we can use either an indicator half reaction to determine the voltage. Before the equivalence point, we'll know that the Fe2 plus and the Fe3 plus, because this is going to be consumed as you go through this reaction. Your overall cell is going to be this right here. Notice you have a standard reference electrode for your E minus. So that one is a fixed voltage right here, right? Based on the standard reference electrode. Right there. Calomel reference electrode, right? So we plug that value in. This other one is going to be your equation here. Your E naught minus the value, we're at 25 degrees Celsius, so we can use simplified Nernst, right? And then it's going to be the reaction quotient. Okay? So every time you add CE, the voltage is going to change, right? How's it going to change? Well, it's going to consume the Fe2 plus to produce the Fe3 plus, right? So some of this is going to go into that form right there. Note that this is not one situation that you can typically just put like minus 0.1 because I put in 0.1 of the CE, okay? That's why you have a voltage monitor. That's why you have a potentiometer. So you can measure that voltage. Is that making sense so far? Fantastic. So the voltage is going to tell you what your reaction quotient is. How much iron, how much Fe2 plus, how much Fe3 plus. So the point which the voltage that you read equals 1/2 the voltage at the equilibrium is going to be analogous to pH equals pKa, right? You remember that. And so at that point, the E plus is going to be the E naught for the Fe3 plus, Fe2 plus couple. Because they're going to be equal at 1/2 the equilibrium point, right? Or equivalence point, excuse me, equilibrium. The equivalence point, these will be 50% this, 50% this, right? They'll cancel, you'll be left with the E naught. Okay. The region 2, this is at the equivalence point, just like all the other titrations, right? Notice this is just like all the other titrations, isn't it? So at the equivalence point, you'll have exactly enough of the Ce4 plus that's been added to react all of the Fe3 plus. So at the equivalence point, Ce3 plus will equal Fe3 plus, and Ce4 plus will equal Fe2 plus. Remember that to make one, you have to transfer the electron from the other, right? That making sense? So notice again, if we look back, Ce3 plus, Fe3 plus, Ce3 plus, Fe3 plus. They have to be equal because to make them, you have to transfer the electron, don't you? Okay. Notice that it is not true that Fe3 plus would have to do something like equal Ce4 plus. It's not true that one of these forms has to be 0, okay? That's a mistake people bring from the acid-base world, because like with a strong base, strong acid situation, which is what you guys are most used to for acid-base titrations, you would consume all of a strong acid or strong base at the equivalence point, right? That's not true here. You won't consume all of any species normally. That would be a very unusual situation, okay? So at region 2, both the half reactions are going to be in equilibrium at the platinum electrode at the equivalence points, and it is convenient to use both of them at this point. So what we get is the E plus is going to have two Nernst equations that we can use. Again, we can just take the voltage to figure these out, but again, the E plus is going to have two Nernst equations. Okay? There's the Nernst equation for the reaction quotient of the iron, right? Has the iron terms. There's the Nernst equation for the reaction quotient of the Ce. We can simplify this somewhat because the Ce3 plus has to equal the Fe3 plus, right? So you can actually trade these in. See that? And the Ce4 plus has to equal the Fe2 plus. Again, we could trade these in, right? Okay. And so the cell voltage would be, again, it would be E equals our E plus, which is this stuff right here, minus the calomel probe. So if we were to substitute these in, remember you can substitute one in for the other, you would get a value of 1.23. You would take minus the calomel reference electrode, and you'd get 0.99 volts for this. So this voltage at the equilibrium point, equivalence point, I don't know why I keep doing that, is always going to be something that you could figure out mathematically, okay? Because this always has to be true, and the Nernst equations have to be true as well, right? And so you can simply substitute one in for the other. There you go. That gives you the equivalence point E plus voltage. If you're using a reference electrode, you have the other one as well. Ta-da! You now know what the voltage should be at the equivalence point, right? So after the equivalence point, the moles of the Ce3 plus will equal the moles of the Fe3 plus. However, there will be an excess unreacted Ce4 plus that you will continue adding in. You don't have anything to transfer electrons from, do you? And so you're no longer going to convert your Ce4 plus. You'll just keep building up concentration of that up to your standard solution, if you have a standard solution. All right, so because the Ce3 plus and Ce4 plus are known, it's actually convenient to use this half reaction right here, which is the Ce form, right? Because those are both terms that you'll know. The equivalence point was already set just from their voltages, right? Just from the fact that they were the half reactions we were looking at. And that's where you get one term, the CE3 plus. The CE4 plus is going to be just what we add past the equivalence point. And so that's your equation for the voltage after the equivalence point. Notice because we know more terms in these equations, they're actually easier math, right? And that's the beauty of math. The more knowledge we have of our system, the easier the math becomes, right? Okay, so let's look at a problem. Suppose that we titrate 100 milliliters of 0.05 molarity iron 2 plus with 0.1 molarity Ce4 plus. We use the cell in figure 16.1. The equivalence point is going to occur when the voltage of Ce4 plus equals 50, volume of Ce4 plus, excuse me, equals 50 milliliters. Calculate the cell voltage at 36 milliliters, 50 milliliters, and 63 milliliters. So personally, I always like to start with the 50 mil, the equivalence point, because the math is very easy at the equivalence point, right? But we're going to go ahead and start at the beginning since, you know, it's the beginning. Good deal. All right, so at 36 milliliters, you'll be 36 out of 50 milliliters of the way to the equivalence point, right? So 36 out of 50 of the iron is going to be in the form of iron 3 plus. 14 out of 50, the remainder, is going to be in the form of the iron 2 plus. Does that make sense? Okay. Everybody see that okay? So, if we go ahead and plug those numbers in, remember the 50s would cancel because it would be out of 50 on both sides, right? So the out of 50s cancel. We're left with 14 over 36, and that would be our reaction quotient. We put that into the equation 16.6, which is the before the equivalence point Nernst equation with the calomel electrode, which we know we're using the calomel electrode because it says figure 16.1, right? We plug that in, and we're going to get, well, the voltage should be 0.550 volts. Anybody have any questions? Okay, so remember, we're using this equation right here, and we know this number. That's 14 out of 36. We plug it in, solve for E, right? By the way, this is why, notice that when I'm talking about these, I'm talking about, you know, we understand this, we know this, we've set up all of these conditions, right? And so it's reduced the amount of mathematical work. So you understand the problems better in analytical chemistry. Like the top 25th percentile for speed on solving problems in this class can solve the homeworks in a bit under an hour, okay? And that's data from thousands of students. The bottom 25th percentile can take 10 hours, 12 hours to do that, okay? The reason for that ridiculous disparity is the more you understand the system, the less work you have to do, right? That's true for every problem in analytical chemistry. The more you understand the system, the less work you do. Okay? So the big thing I always recommend is whenever you start a problem, list out what you know from a system, see if you understand it well enough. If you have no idea what the hell your system is, you have no idea where to go, come back to that problem later if you have time, okay? If you understand your system and you know directly where you should go, then do the problem. It'll be very easy. It'll be very quick, okay? Once you understand a system, there aren't actually long, difficult problems. Like the math for any of these problems can be done in usually 10 minutes at max, okay? That would be a very long problem if you understand the system. If you don't understand the system, it could take you hours, right? Again, notice we cut out all our work by doing this part right here. See that? Okay. So at 50 milliliters, well, we know the voltage at the equivalence point has to be 0.99. We actually already solved that, didn't we? And that's true for all of these redox titrations. Their Nernst equations have to be represented, have to be true. And then this also has to be true, that each side of the equation has to be equal, right? So the iron Ce on one side has to be equal. The iron Ce on the other side has to also be equal, okay? At the equivalence point only. So at 63 milliliters, this is after the equivalence point, right? So after the equivalence point, we know that 50 milliliters of the Ce was converted into the Ce3+, the product, right? Everything beyond 50 milliliters is going to be excess and cannot be converted at all because we have no source of electrons left. We've used it all. So that means 63 minus 50, which is 13 milliliters of Ce4+ that we've now added. So we can plug these into our numbers for our reaction quotient. The Ce3+ will be 50. The Ce4+ will be 13. Notice we don't need the concentrations because the concentration would be the same on both sides, right? So we can cancel them, okay? So the volumes are all we have to do is just plug it in the volumes. Isn't that nice? And this is going to give you an E equals 1.424 once you plug it into this equation right here. Okay? Do you see how fast these problems can be? Like I explained every part of this, but seriously, this took like half a minute here, half a minute there, half a minute there. How the E naught is 0.767 for the Fe3 reduction. I'm going to go back to right here? Yeah. Would you still be using that same exact equation because E naught's still the same for that reaction? Okay, so there's 3 regions that you have to concentrate on. So for region 1, you only have the Fe. That's your Nernst equation that matters here, okay? And so you use the Fe Nernst equation here, and it solves out to this, right? We've put these 2 terms together, but if you have a different standard electrode, make sure you swap that out, okay? So that first region is going to be dependent on the Fe reaction quotient, okay? The second region at the equivalence point, it's not actually, you don't actually need a reaction quotient at all, okay? Because due to the fact that these are equal, you should plug in one Nernst equation into the other. You literally solve it out so this is on one side, and then you plug that in and you have no variables. They're all constants, okay? See, this is equal to this one. So see, this one right here is equal to that. So you plug this in, so you have our NCE terms here, or Fe, I don't care. Fe on both of them, Ce on both of them, whatever, right? You solve it out, so this part, one of these reaction quotients equals the other, and you plug that in. If you do that, it'll solve all the way down to a constant, because it's a constant. At equivalence point, these are always constants, okay? Because this is literally basically this is from the electronegativities. This is literally from the E naughts, how well one takes electrons from the other, okay? It doesn't matter what the concentrations are or whatever, it doesn't matter. Because at equivalence point, the concentrations always have to be the same ratios, okay? Okay, the region 3 is going to be dependent only on the CE. There is no voltage changes for the iron anymore. You can't have any voltage coming because that's a change, right? You consumed all your iron. So that's done. Region 3 after equivalence point is only based on CE, reaction quotient. Okay? There is no more FE. That's not changing, that's done. Remember, a voltage has to do with a change. Okay? You have to, it's like a velocity. You have to be moving, right? You have to be moving electrons. So if you can't move electrons, there's no voltage. It's done. Think of it as a dead battery. Now all you have is the CE reaction quotient for your battery, right? Okay. That making sense? That better? So at the 3 different regions, it depends on different things.
Well, I was just wondering about this. Are we just using the same E0 values as earlier? Is this the same exact equation?
Oh, like the E0 here?
Yeah.
Yes. Those are always the same E0s. They can't change because they're the same half reactions.
Yeah.
Yeah. Yeah, they can never change.
Actually, and then you go down to the next slide. Right there. What's the minus
Here?
2.241? Is that just
The calomel.
or in this equation?
No, period. The calomel electrode isn't going to change. That's why it's the standard reference electrode. Yeah. If it was changing, then you wouldn't be able to do any of this work. So that's actually why that's a standard reference electrode, rather than being, you know, another electrode or something coming in here, rather than being like a platinum wire. Is you have a standard reference electrode that you're measuring everything against. And that gives you your 0, right? You don't use an SHE because it's difficult to use. It would be a pain in the ass to use. So you use a calomel electrode because it can store better, it's better, easier to operate. And effectively, it doesn't matter, right? Because you just subtract the same number every time. That better? Okay. We're going to kind of pick up a little bit, and I'm just going to go over some of the definitions and stuff. If there's problems that you're having issues with, to be honest with you, all the problems are kind of the same damn thing over and over. Okay? Yeah. I mean, it's just Nernst equations over and over. It really is kind of it's a boring chapter, but it's important and this is actually a huge growth field, by the way. This is how they make those little chips that they've been selling for like 25 cents in Africa to test for HIV and stuff. Or lead poisoning or any of that stuff. Yeah. And they're getting good enough that you'll start seeing them in America in the next 10 years. They just need to go through the testing phase. So a redox indicator changes color when going from an oxidized to a reduced state. Yes, this is all indicators. I mean, that was literally phenolphthalein did the same thing, didn't it? Yeah. So anyways, this right here is an example. This is the oxidized ferroin. It's pale blue. You write these with a abbreviation of the name, so LN right here, or IN, excuse me. Yeah, IN. Oxidized for the oxidized state, right? And then you'd write reduced for the reduced state. There you go. Okay? This one goes from pale blue to red. There are a huge variety of these. Remember that when you have color changes, the color change is going to occur over a range, which will be E equals E0 plus or minus, so that gives you your range, right? Plus gives you one end, minus gives you the other. That is the, notice the value there. The Nernst equation, right? You're looking at a factor 10. See that? So factor 10 10 over 1 in the log and 1 over 10 in the log. That would give you this value. Okay. Same as the acid base, right? Like a buffer solution. It's over n, by the way, which is the number of electrons. Keep that in mind, because if you have an indicator that has 2 electrons in here, that's going to have a much smaller range. Okay? Oh, right here. Yeah. The amount that you have to add or subtract to have a difference in the oxidation state. So redox indicators will give satisfactory endpoints when the difference in the formal potential is greater than or equal to 0.4 volts. If you have a difference in the formal potential that's lower than that, this is going to be lower than limit of detection. Okay? It's unlikely you'll ever see anything at all. Okay, so these are some of the different redox indicators. It's E naughts, and this tells you the oxidized color and the reduced color. Notice that it is, you can go both ways. Like you can go from oxidized to reduced, or you can go from reduced to oxidized, right? It entirely depends on what the metal species that you're looking at does, what the reaction you're trying to monitor does, okay? If it's giving electrons, you'd end up going to the reduced state, right? And you'd want to start with mostly oxidized state. Or at least have it 50-50, which would be on the E naught, right? Like a buffer, okay? They work a lot like a buffer solution. That's actually how all indicators work, a lot like a buffer solution. And that's why they work best around a range. Okay, so finding your endpoint. Right here, we're looking at a gram plot again. I mean, you guys are probably sick of these by now. You probably are like, why is there so many fucking titrations? There's little tiny differences, right? Like for these, they're actually easier math because the equivalence point is always a constant, isn't it? Yeah. So that is nice. Anyways, here's the gram plot again. It's going to use the data from well before the E, the equivalence point volume, to locate your equivalence point volume. And this actually is a lot easier in these cases because you can monitor voltages, right? So that makes life a little easier. So right here, this is your volume. And then don't forget, this is going to be this voltage times 10 to the power of number of electrons, E, over that Nernst equation constant. Remember that? Notice this is just solving the Nernst equation for the voltage to be this term on one side. Okay. So you have a bit of a problem in these that just like the other titrations, as you get closer to the equivalence point, your data becomes less and less accurate, right? Because you get these large changes as you get close to the equivalence point, okay? And again, this is especially true in these cases because your electrodes are slow. You've seen the pH meter. Remember when you used those? You had to wait for like a minute sometimes? That's an electrode, okay? The electrodes can be very slow to detect. So they're slow to equilibrate, reach their equilibrium, and therefore they're slow to give you an accurate reading. If you get close to an equivalence point, you're almost certainly going to miss it, okay? So what you should do is collect data well before the equivalence point, put it into a gram plot, get a linear relationship here, the linear fit to that data, and then you graph it with the voltage times the 10 to the power of, N E divided by this versus the volume down here. Please be aware the V's here. I'm sorry, volume here. I don't know why I keep saying voltage. Volume times 10 to the power of versus the volume here. Okay. Once you plot it, this x-intercept here is your equivalence point. Everybody okay with that? Notice this is just like all the other gram plots. If you go back, you'll see that we've done gram plots pretty much every titration chapter in one form or another. So this is actually a very common analytical procedure. Many of these analytical procedures are actually based on the redox titrations of iodine because it's easily visible in its redox states, and it's very reliable. It's very easy to mix up solutions, and it's cheap. Starch is the indicator of choice because the starch iodine complex is an intense blue color. It's very easy to see, and it's very different than any of the other colors in these. This is starch, by the way. This is the iodine binding to the starch, which causes that intense blue color. That's what it looks like if you look downwards. Okay? You guys have done this, right? Use an iodine starch? No? A little bit sad. A little bit sad. Anyways, you can actually do this at home. You can get starch and iodine solutions, providine, mix them together, and you'll see it. Anyways, that's probably the most common redox titration you'll see, is some usage of that, paired with something else maybe. Pre-oxidation, powerful oxidants that can easily be removed after pre-oxidation. So this right here would be an example of pre-oxidation. Peroxy disulfate with silver as a catalyst. The excess reagent is removed by boiling the solution after the oxidation of the analyte. The silver 2 oxide, this is going to dissolve in acid to give the silver 2 plus, which can be removed by the boiling. Another example would be solid sodium bismuthate. I hate that fucking name. It hurts my mouth. The excess solid is going to be removed by filtration. In this case, you'll form solid and you can remove it through filtration, right? Hydrogen peroxide. This is kind of a pain in the ass to keep at a consistent concentration. It tends to go down in concentration as you keep it in your storage. But, you know, if you're a bigger lab, this is not a problem. You can just make fresh batches all the time or order fresh batches every day. Yeah. Yeah. For like a lab like us, this is a son of a bitch to keep. Because we don't use a bottle over like 5 years.
So if you have like cleaning, you know, for like cleaning your cut or whatever, so like not do that here.
Yeah. If you keep it in the freezer, it might last for a few years. But if you keep it in your cabinets, it's probably done for after a few months.
Oh, really?
Yeah. Yeah. Now, you only actually need like a 5%. So you may get, if you buy a 30%, you may be okay for maybe a year. Yeah. But it's, yes, it degrades pretty fast. I mean, you can test it. If you use it, well, I wouldn't use it on your blood necessarily because it could grow stuff in it. But, you know, you can test it against different stuff and see if it works. You should be able to put it with like metals and it'll oxidize. It'll produce bubbles, right? Hydrogen bubbles. So. Huh? Yep, you got it. And see how it works. It certainly won't work as well as when you bought it. But it might still be like a 1-2% if you've had it for a few years. And you don't need that much. I mean, it's pretty effective oxidizing agent. This is a very good oxidant in basic solutions. It can reduce, for example, chromium Cr2O7 to Cr3 plus, or permanganate down to Mn2 plus. It spontaneously disproportionates in boiling water, which is this right here, and it forms the O2. Okay? And it does that all the time, actually, if you let it be warmer, basically even close to room temperature. Even in the fridge, it'll slowly react. So, a disproportionation reaction is going to be one in which a reactant oxidizes and reduces itself. So you get two of these. One is the reducing agent, one is the oxidizing agent. They react together. Kind of like water does, right? Where it autoionizes. This is just a redox reaction instead. This is a pre-reduction. So stannous chloride SnCl2 can reduce iron 3 plus to iron 2 plus. Notice this is similar to what you were doing before, where you want to get it in one state. So you want to get it all into iron 3 plus, or you want to get it all into iron 2 plus, so you can do the reaction. Okay? This can be done in hot HCl. The excess reductant is going to be destroyed by adding mercury chloride. This is not one I would recommend anymore, because the mercury chloride is very expensive now, and very expensive to get rid of. Mercury anything is not a good way to go these days. They have put a lot of regulation into mercury, and it gets very expensive to do unless you're out of the United States, or you have very specific pathways to get stuff. Chromous chloride is sometimes used to pre-reduce an analyte to a lower oxidation state, of course, because that's reduction. Excess Cr2 plus is going to be oxidized by atmospheric O2. This one's nice because you get half your atoms from the atmosphere. Gotta love that. Chromium 4 plus, by the way, is actually hexachroma. Is actually highly toxic, if you're curious. Chromium 2 plus is a necessary mineral you need in your diet. Like chromium 4 plus causes every form of cancer you can imagine. Horrific diseases, kills all life in the area. Chromium 2 plus, you need in your diet. It's in your vitamins. There's a company, by the way, that tried to make it so nobody sued them before the statute of limitations by telling a town that they had chromium 2 plus leaked into their water, which is a health supplement, and they leaked chromium 4 plus and gave hundreds of people horrific diseases and killed dozens of them. It probably killed hundreds, actually, over time. But yeah, Aaron Brockovich, by the way, if you ever want to look up the story. They made a movie on it that's not entirely accurate, but whatever. Sulfur dioxide and hydrogen sulfide are mild reducing agents. These are expelled by boiling an acidic solution. Notice all of these need some form of neutralizing or expelling them, right? When you're done with that, you don't want another half reaction going on in that titration, do you? Okay? And that's why the second part is how to neutralize everyone, all of them. All right? This is a very nice one, by the way. It just stinks. Works well, though. All right, so an important pre-reduction technique is using a packed column with a solid reducing agent. This is very convenient because it never leaves you with a half reaction at the end, right? So this is the fourth pre-reduce. Jones reductor. It's a column packed with zinc, coated with a zinc amalgam. It's not very selective in its reduction, so if you have multiple species that could be reduced, it's going to reduce everything, okay? And that's not surprising. I mean, it's a metal, right? Metals lose their electrons to damn near anything, right? And zinc particularly is a pretty good reducing agent. Walden reductor is a column filled with solid Ag, silver, and 1 molar of HCl. It is more selective than the Jones reductor. This is typically what they look like, by the way. You load an analyte solution, you have a solid reductant, and then some sort of glass disc or something to keep that in place so it doesn't pour through. And then your analyte solution will go through, get reduced, and come out the other end. Notice you can actually directly use this for titration if you needed, but you have to be very, very careful about this, because I would not directly use it for a titration unless absolutely necessary, okay? Because this can start shifting and give you readings that are not as good as you would want. Let's put it that way, okay? Potassium permanganate, this is a strong oxidant with an intense violet color that goes to brownish color once it starts reacting with things typically. But you'll see a lot of them in brownish color because people leave them in clear glasses and the light causes them to react. It's reduced to Mn2+ in strongly acidic solutions. This is the reaction here. That's E0. In a neutral or basic solution, you'll get solid MnO2. This is the product. This is the one you see a lot, by the way. You guys probably saw this, right? You guys never seen potassium permanganate? Should have used it in Gen Chem. Yeah, typically I keep them in brown bottles. And yeah, typically they're in a neutral or basic solution, and then you put it into some sort of acidic solution and it starts reacting. So in strongly alkaline solutions, you'll actually get a green manganate ion, and it's quite distinct looking. It's kind of neat looking. So you may have actually seen this if you ever looked at our waste bottles. That happens quite often in the waste bottles, because we tend to have basic solutions for our waste. Potassium permanganate, this is not a primary standard. This has to be standardized by titration with typically sodium oxalate. And you remember your primary standards versus, this is not one, it's too reactive. It's going to oxidize everything around it all the time. You cannot keep a solution on your shelf for any period of time and expect it to have the same concentrations, be the same as it was when you put it up there. Okay? Damn stuff reacts all the time. With everything. If you remember your organic chemistry, it actually splits double bonds, doesn't it? Remember that? It was one of the oxidizing agents. You could fully oxidize double bond. What time is it, by the way? We done? Okay. I'll see you guys next time on this. I was a little slow today.